A pulley system is made up of two rigidly connected concentric solid cylinders of radius 0.8 and r over 3. Okay? The moment of inertia for the pulley system I is 5.2 kilograms meter squared. Okay, so that makes sense. They just give us the moment of inertia so we don't have to try and figure it out, which is nice. A mass M2 is attached to a massless string wrapped around the outer cylinder, while mass M1 is attached to a massless string wrapped around the inner cylinder, as shown in the figure below. Okay, so they have different radiuses. What must be the mass of M2 for the system to remain at rest? Okay, so when you see something like at rest, what we're going to say is, well, I'm going to say equilibrium, but what I really mean here is, so mass 1 is going to create a clockwise torque. So I'm going to say torque clockwise equals torque counterclockwise. And torque equals R cross F. And so what we're going to have is R, since R is, I'm going to draw R like this. That way it's obviously perpendicular. Oh, right there. So for this one, it's going to be R over 3 times force of gravity, which in this case will be, we can do is mass 1 times gravity, which will equal R, this R right here, times mass 2 times gravity. Now, just intuitively, I'm going to think that mass 1 is going to be greater than mass 2. So looking at this, we can do some canceling real quick. So gravities go away, R's go away, which is convenient. And we have mass 2, equals mass 1 over 3. Which is, let's get the calculator out. Calculator, on, clear, whoop. Mass 1 is 5.8, so we do 5.8 over 3, and we get 1.93. So bam, right here, D. This will be the answer. Not too bad, not too bad. You just balance the torques. Torque clockwise, torque counterclockwise, set them equal, and you're good. Okay, now the string to mass M2 is cut. What is the acceleration of A, so linear acceleration of mass 1? Okay. So this is basically, what we've been looking at here is kind of like an Atwood machine. You balance the forces on each side. But now we have a pulley here. So this thing is gone, not providing a force. And we're going to look at this in terms of, we're going to say there's a tension here. So we have a tension pulling up on the mass. And we have a force pulling down on the grass. We'll call it force gravity. And so if we look at the block, kind of free body diagram idea, we have sum of all forces equals mass times acceleration. This will be mass of the block. And this will be the sum of all the forces, as we wrote right there, which will be force gravity minus tension. Okay, so that's one equation. Now we're going to do the same thing, but with the pulley. Now before we, with Atwood machines, we look at one block, look at the other block, and kind of put them together. And then try and, kind of get the tension to cancel out, system of equations type thing. Well, we're going to do something similar here. So we'll say sum of all torques equals moment of inertia times alpha. And we know that the sum of all torques is going to be R cross F. This is for each individual torque. But in this case, our force is going to be this tension right here. So that's going to be, and this R is actually going to be R over 3. So keep that in mind. So R times tension, IA, equals R times tension. And then one other thing, so that we can kind of clean this up a little bit, we know there's a relationship between angular acceleration and linear. So we say X equals R theta, V equals R omega, and acceleration, linear, equals R alpha, angular acceleration. So if we want to find out what alpha equals, we have alpha equals A over R. Boom, like this. So if we want to rewrite this, this would be IA over R. Now, this is one of the parts we want to be careful, because your first thought is going to be to write AR here, not instead of A over R. Because your soul is calling out to you to cancel these R's, which is not what happens. Those R's do not cancel. And what you get is tension equals IA over R squared. So don't let those R's cancel out. They're important here. And kind of from an intuitive feels point of view, you can think that moment of inertia, you see over here, its units are kilograms meter squared. And so when you come over here, you're going to have kilograms, it looks like an R. Okay, kilograms meter squared. You divide by meter squared, you're left with kilograms, which kind of makes sense because then you have a mass times acceleration, which would be a force, which we're modeling here as tension. So all of that is just to try and keep you from canceling out those R's and leaving it. You want to leave it like this. Okay, I'll take this equation, plug it into this equation. We have mass of our block times acceleration of the block attached to the pulley system. This is going to be force times gravity, which I'm going to call mass, just B for block, times gravity minus IA over R squared. Okay, we got that. So now what we're trying to find is this A right there. So we can rearrange. So we have M. I'm just going to leave it as M now. I know I keep simplifying. First started as block, then just went to B. Now it's just going to be M. So confusing. I need to work on my boardmanship. Over R squared equals mass times gravity. Factor out the A. Here we go. And acceleration equals mass times gravity all over M plus I over R squared. Okay? And we can solve this. Mass, I think it was 5.8. All the way over here. 5.8. Yes. So mass was 5.8. We had gravity, which we're going to assume is 9.8. We can use 9.81 if you prefer. Then we'll have 5.8 for mass again. This was 5.2, moment of inertia. And then R is 0.8 over 3, which I think is like 0.266. Is that right? Maybe there's a 7 involved. Let's figure this out. On 0.8 divided by 3. Yep, 0.226. Okay. So this will be divided by 0.266 squared. Yep, that looks reasonable. So solving this, I'm going to start at the bottom right just because that's looks like it'll be easier. Squared 5.2 divided by second answer plus 5.8. Yep, that moment of inertia is dominating that part of the equation, which is 78. So we'll do 5.8 times 9.8. I'll throw in a 1. Divided by second answer. And we get 0.7209. 0.7209. So this is the dominant part of the equation. And this will be meters per second squared. Check out, see what the possible answers are. Zoom out. So messy. So messy. 0.72 right there. So E right there is going to be the answer. So to backtrack, kind of like what we did that probably the hard way. This is really easy to mess up. So as kind of a dummy check to look back and see what we did and make sure it makes sense. Remember with the Atwood machine, you would kind of get the sort of situation where you had the net external force on top, net external force, and then on the bottom you would have the sum of masses. And that's kind of what we have right here. Except this time we have the moment of inertia divided by R squared, which kind of makes sense as we talked about earlier from a dimensional analysis point of view. Kind of the way of converting a moment of inertia to a mass, kind of flaky, is by dividing by R squared, where R is where the torque is here. In this case it would be R over 3. So the idea here is you have total net external force divided by the sum of all masses. And if you think of this in just as a block falling, this would make sense because the mass times gravity on top would be total force divided by the mass, and that would just give you 9.8. It's like, oh yeah, things normally when they just fall, they fall at 9.8. But the idea here is we have the force of this block pulling it down, but it's accelerating a larger mass. And the analogy from an Atwood machine, which you did was all just linear with a massless pulley, now you don't have a massless pulley. In the moment of inertia that this pulley is giving you, the way you convert that, so to speak, to a linear mass is dividing it by r squared. So if you're in a hurry, you really want to get this problem done quickly, which, for a test might be true, this is the kind of equation you're going to use. And you can just kind of throw it in there. Maybe it works, go for it, and maybe. But this is the formal way of going through and how to solve this problem. So I hoped that helped, and I will see you on the next problem.